find the areas of them, so width times length, length times height, and width times height, and you've got those areas shown below. I've chosen the materials I had in the Sabine graph for each of my surfaces. So wood being the floor, beg your pardon, wood being the ceiling, carpet on concrete as my floor, brick as walls, and I also have glass windows. With all of them taken into account, the surface's coefficients equal 8.4 for 125 Hertz, and you look down, so floor is 0.6, 0.45 for the walls on one wall, and where I've included glass windows, I've had to subtract their absorption value off of the walls area. It's important to include them. So looking at that, that is essentially my workings out. Once I add up all of the values, I have total absorption, and with that I divide the volume by the total absorption, which you can see on the right hand side. I'm going down in stages. So volume was 90 meters cubed divided by 125 Hertz total absorption, 12.26. The answer is 7.340. And then what we had, the R260 formula was K times volume times A, where I'm doing it in meters in this example, so K equals 0.161. So in seconds, RT60 is 1.181 seconds, which is okay. It's not bad. It's workable in the efforts to lower that. It's not too bad. So once you've done this equation with the other frequencies we saw, which I've done here, I see that it's not too bad. What you want ideally is 5 half a second. And my room's, the room that I've got isn't too bad. The higher frequencies are obviously better, being around 0.5. However, it's the lows that need to be sorted out in this room. Okay, yeah. Like many methods, there's not always going to be one fully right way to do things. The problem with the Sabine equation is that with coefficients above 0.3, it doesn't handle them as well as what I'm about to talk about, which is the Norris-Earing equation. I hope I pronounced his last name right. Yeah, it performs better coefficients above 0.3. The formula itself is RT60 equals minus 0.161, which is the K again, times volume divided by S, which is total surface area of the room, and then you have to hit natural log on your calculator, and then 1 minus alpha, where alpha is the average coefficient of your surfaces. So looking back on the previous one, perhaps I'm going to go through what using my calculator. We'll do a bit of Owen's equation. So what you start with, you have to make sure with RT60 equals minus 0.161 times 90, because the volume is 90. That's going to be well small, isn't it? Hang on 1 second. I want to fit it all on the slide. Okay, so V divided by S logarithmic 1 minus alpha. Okay. So alpha of the room that we had previously is going to be 1.5325, as it is the total number of surfaces I had, coefficients added up, and then it's the average. So there were 8 surfaces in my room. I divide that, I get 1.5325. And the next thing you want to do, as it says, you start on the right hand side of the equation, which is in brackets. So then you divide that, you take away 1 from alpha, which gives you 0.5325. And then now you want to start from the left hand side. So you times minus 0.161 by V, which in my case is 90. So that's minus 14.49. And then you take the total surface areas squared in meters, which is 126 meters, I believe. Meters squared. And then times that by the natural logarithmic scale, which you do the 0.5325 and then press the log button, and you will have the number minus 0.6301 minus 14.49 divided by 126 times 0.6301 that we have now, minus 14.49 divided by, so now that we have that number times 126 times divided, so 0.6301, we have to do the 126 times 0.6301 first, which gives you minus 79.3926. So you divide the minus 79.3926 by minus 14.49, and you equal, well, the Norris-Erring method gives you a reverb time of 0.74 seconds at 125 Hertz. The numbers are pretty similar in terms of reverb time. However, this version, it's based on averages. They both have their downfalls, because it's not, you don't get an accurate response with averages. But there's also other methods which are great, but